We have seen previously that the sum of this infinite series, 1 over k squared, is at most 2. So we obtained this estimate using the integral test. Now it turns out that in fact, the infinite sum of 1 over k squared is equal to pi squared over 6. And this was probably the first computed by Euler. And this uses something called Fourier series. So this is a non-trivial equality that we cannot discuss. We don't have sufficient tools to discuss it within this course. Now, the important part is that the estimate that the integral test gave us had nothing to do with the true value of the sum. Okay, so the only thing you can say that, well, the true infinite sum is less than or equal to 2. That's all that we can determine from the integral test. But turns out that we can actually use the ideas from the integral test in order to estimate how well partial sums of an infinite series approximate its infinite sum. Okay, and the way we'll do it is the following. So we will think about the difference between the infinite sum of a series. So suppose we are given a series. Okay, let's start from the beginning. Given a series, sum of ak, k from 1 to infinity. Suppose it is a convergent series. It has no negative terms, and its infinite sum is s. Right? So we don't know what s is, but it's just some finite number. Okay? Consider the differences between s, the true value of the infinite sum, and the partial sums. Right? So what this is it's the difference between the infinite sum of ak's and the finite sum of ak's for k from 1 to n. Okay. And this is what we'll call the nth remainder of our series. So it gives the remainder between the infinite sum and the nth partial sum. And so if we rewrite this difference, we'll get that it's equal to the sum for k from n plus 1 to infinity of ak. So this is the expression for Rn that we will need. Now, applying the area argument, so basically what we are thinking about is this is the sum of the series starting from some point. So we're going to compare it to the area under the graph of f of x, which corresponds to this sequence starting from that value of x. But in order to do that, we want to make sure that we are in the position to apply the integral test. So let us recall the assumptions necessary for applying the integral test. And so this will be the so-called remainder estimate. So when you are told to estimate a remainder of a series, it means that you have to apply this statement that we're about to formulate. So suppose we have a function which is, again, continuous, positive, and decreasing on x bigger than or equal to n bigger than or equal to 1. So it has these properties starting from some number n, positive integer n. And suppose it generates the sequence ak by being evaluated at the numbers k. So here k are at least n. Okay, then Rn so let's put it this way. Then for Rn, given by this formula, the sum for k equal from n plus 1 to infinity of ak, there holds Rn is at most the integral of f of x from n plus 1 to infinity, and at least the integral from n to infinity of f of x. So here is what we did here. So we're basically thinking about the graph of f of x again, but now we're thinking about it starting from the point x equals n. Okay, so we have some point x equals n, and we consider the graph f of x like so. It's continuous, positive, and decreasing, so its graph looks like that. Now, as before, we look at the rectangles that correspond to terms of our series, but this time the terms are only starting from the number n plus 1. So the reason I put n in this picture will become clear in a moment. So you have this picture, and then you estimate the whoops, I have this backwards. Should have n plus 1 here and n there, actually, because this integral is smaller. So as I will explain in a second. So you see that the area starting from the x equals n and to the right is larger than the area starting from x equals n plus 1 and to the right of that. So let's say the pink area is larger than the green area. Right? And so the pink area corresponds to this integral. The green area corresponds to this integral here. Okay, now what we do is we estimate this tail of our series using either rectangles of this form, right? So they are contained in the pink area, and so that gives you the right inequality, or alternatively, we look at these rectangles, right? And they contain the green area and correspond to the terms of our series again. So it's taking these heights, right? So you take this height, which corresponds to the a sub n plus 1, this height, and so on. And then on each of these lines, you draw a little rectangle, and you draw it either to the left or to the right. All of such rectangles will have width 1, meaning that the areas are exactly the values of AKs. And using these area arguments, you obtain the two estimates, like so. Okay, so why is this useful? It's because now, using the integral estimate, we can look at a partial sum of a series and be able to tell how well this partial sum approximates the infinite sum. So obviously, we're never going to be able to evaluate the infinite sum. We cannot add up infinitely many numbers in a constructive fashion. What we can do, though, we can add up finitely many numbers and then evaluate an integral that will tell us how good an approximation to the infinite sum we have. And so let us now discuss an example, number 6, if I'm not mistaken. That's right. So let's consider the example 6, in which we have to do a couple of things. First, approximate the sum 1 over k cubed, k from 1 to infinity, by s sub 10. Right, so this means instead of looking at the infinite sum, we are looking at the sum of the first 10 terms in this series. Then what we will do is we will determine the error of this approximation, or rather estimate the error of this approximation. In other words, we will say, okay, we added up 10 terms, how bad an estimate is that? What's the maximal error that we can make in this way? So that's point A. And in point B, we will determine how many terms are necessary for the precision of 10 to the negative fifth. Okay, so in other words, how many terms in this series do we need to take to be able to evaluate the sum of the series up to 5 decimal places? So this is what we'll do in the next video. So we'll postpone the solution of this example to the next video to keep them short.